Hey guys, welcome back to Civil Learning Online. And today in this video, I'm going to discuss about one of the most important topic from the exam point of view, that is cantilever method. Here I have selected a numerical and I have solved the same numerical using the portal frame method. Link is in the description, and I am solving that same problem using the cantilever method so that it will enhance your concept based upon the solution of approximate method of analysis of frame. There are basically two methods. One of them is portal frame method, another one is the cantilever method. I hope you know these things, and without any further delay, let's get started. And guys, coming toward the solution of the numerical based using the cantilever method, here I have selected a portal frame which has three stories: first story, second story, and third story, and each of the story are loaded with the lateral load of 12 kilonewton, 24 kilonewton, and 48 kilonewton, which is clear from the diagram. And the span of AB, BC, CD is 5 meter. Similarly, and the height of the each story is 6 meter, which is clear from the diagram. And for solving any numerical based upon the cantilever method, one must know the assumption for cantilever method. If you have watched my previous video about the portal frame method, then you will find that there are also two assumptions for solving any numerical based upon the portal frame method. Similarly, here also cantilever method has some assumptions, and I am going to take you through those assumptions one by one, and then we will also see the application of these assumptions while solving the numerical. And as the this numerical will be solved step by step. So if you are learning this method for the first time also, this is going to enhance your concept. One is point of contraflexure occurs at the middle point of the various member. So basically a frame comprises of the two members, that is vertical member is called column and the horizontal member are called beam. So the point of contraflexure will be at the middle point, means the point where the bending moment will change its sign, means positive to negative or negative to positive, that will be at the center of each member. Suppose AE whole span is 6 meter, then its contraflexure will be at middle of AE, that is 3 meter. Similarly, for EF, this is beam and the span is 5 meter, so its point of contraflexure will be at half of the 5 meter, that is 2.5 meter. And same will be for each and every beam and column, that will be at middle portion. Similarly, our second assumption is direct stresses in the column are proportional to their distances from the centroidal vertical axis of the frame. This second assumption will be more clear when I will start solving this numerical. And first I will apply. First of all, we need to find the point centroidal vertical axis of the frame, and after that we will go through the concept and it will be more clear. So guys, here comes step 1, location of the centroidal axis of the frame. This whole frame has a centroidal axis, and we need to locate that centroidal axis, because it is mentioned in our assumption second also, because our direct stresses of the column will be proportional to their distances from the centroidal vertical axis. For that reason, we need to calculate the centroidal vertical axis. And let us assume that this is our reference column. AEIM is our reference column, and with reference column we have centroidal axis at distance x bar. So let us assume that our centroidal axis is at distance x bar from our reference column AEIM. So I am going to write it here. Now, after this, what we need to do is we have to do one more assumption, that the distance of this first column is at distance x1 from the reference column. This is at distance x1 from the first column. Similarly, distance of the second column is at distance x2 from the centroidal axis of the frame. Similarly, distance of this third column be at distance x3 from the centroidal axis of the frame. Similarly, again assume that the distance of this fourth column is at distance x4 from the centroidal axis of the frame. Second column has a distance x2, third column has x3, first column has x1 from the centroidal axis of the frame, which is at distance x bar from the column AEIM, which is our reference column. Now, what we need to do is we have to find the value of x bar. How we can find? We will apply the same condition what we use for calculating the moment of inertia. There are 4 columns, and let us assume that each column has a uniform cross-sectional area, that is A. So what we will have here, 4a multiply by x bar, means sum of cross sectional area of each and every column. There are 4 column total, so 4 times a multiply by x bar equals to this is our x1, and the area of first column is a, so a multiply by distance of the, this is our reference column, so we need so the distance of the reference column will be 0, and as here, listen guys, see here, this is our first column, and the first column, and this is also the reference column. So the reference for reference column we have area a, and the distance of this reference column will be 0, because we do not need to move and at any other distance from this column, so a times 0 plus second column is our, again area is a multiply by distance of the second column is 5 meter from this reference column, so it is multiplied by 5 plus this is our third column, so third column again area is a, and the distance from this reference column is 5 plus 5, so 10 plus distance area of this third column is again a, and the distance of this third column from this reference column is 15 meter. So from here we can find the value of x bar equals to 15 plus 10 plus 5, means 30a divided by 4a. From here we will get x bar equals to 7.5 meter. Now we have got x1, and from the diagram it is clear that x1 is equal to x bar, so we will have here x1 is equal to x bar equals to 7.5 meter. Now time to calculate x2. These are the distances of the centroidal axis. We have calculated the value of the centroidal axis of the frame, that is 7.5 meter, and the distance of the centroidal axis from the column 2 is x2, so we will have x2 equals to whole 7.5 meter minus this 5 meter. We will have this much span is 7.5 meter, subtract 5 meter, we will get 2.5 meter, that is the distance x2. So x2 equals to 7.5 minus 5 equals to 2.5 meter. Similarly we have x3 equals to, we need to calculate the value of x3, and this much span is 5 meter, and see here span BC is 5 meter, and we know that distance from here to here it is 2.5 meter. So what we need to do is 5 minus 2.5, and the remaining portion, remaining value we get will be x3, so x3 will be again equals to 2.5 meter. Similarly if we calculate x4, and see here guys, whole span is 15 meter, and we have got x bar, whole span is 15 meter, so whole minus x bar value is 7.5 meter, this whole minus this portion, we will get x4, and x4 is the distance of the fourth column from the centroidal axis of the frame, that is 15 minus 7.5, we will get x4 equals to 7.5 meter. We are getting the similar value, it is because the span are same. Whenever it is asked in exam, this value may be, if this spans varies, value of this span are not similar, then this value will also not be similar. Now here comes the application of our second assumption. See here, what is that? Now the second assumption is that the direct stresses in the column are proportional to their distances from the centroidal vertical axis. Means if we assume that the direct stress in column AE is V1, similarly direct stress in the column BF is V2, here V3 and V4, then it says that V1 upon x1 will be equal to V2 upon x2 will be equals to V3 upon x3 will be equals to V4 upon x4. That the direct stresses are proportional to their distances. This x1, x2 are the x4 are the distances of the these columns from the centroidal axis, and this is the what the second assumption says. And using this assumption we are going to proceed with the numerical and find the final answer. So what we need to do is we have to resolve this V2, V3, V4 in terms of V1. So if we write a line here, taking first and second ratio, we will have V1 upon x1 equals to V2 upon x2. Now put the value here, we have V1 upon value of x1 is 7.5 equals to V2 upon x2 is 2.5. So we can rewrite it as V2 equals to this is in division, so it goes this side, then it will be in multiplication, so V1 upon 7.5 multiply by 2.5. Oh, it was not visible, sorry for this. See here, V1 is this, we need to resolve V2, V3, V4 in terms of V1. So we will take first two ratios. So V1 upon 7.5 equals to V2 upon 2.5. So now we will have V2 equals to V1 upon 7.5 multiplied by 2.5. This 2.5 is in division, so it goes this side, so it will be in multiplication, and further it is same. So V2 equal, we'll get V2 equals to 0.33 V1. Now again we will rewrite here, taking first and third ratio. So we have first and third ratio is V1 upon x1 equals to V3 upon x3. Put the value V1 upon value of x1 is 7.5 equals to V3 upon value of x3 is 2.5. So from here we will have V3 equals to V1 upon 7.5 multiplied by 2.5. This 2.5 is division, this goes that side, then multiplication. So we will have, therefore V3 equals to again the value will be same, 0.33 V1. Now take first and fourth ratio, because we need to again resolve the V4 in terms of V1. So taking first and fourth ratio. So if we take first and fourth ratio, that is V1 upon x1 equals to V4 upon x4 equals to V1 upon x1 value is 7.5 equals to V4 upon x4 value is 7.5. So from here we will get V1 equals to V4. Now move to our step 2. So guys, here is step 2, and in step 2 we need to calculate the axial forces in the column of story 1. And how we can do this? See here. So for calculating the axial force on column of story 1, all the forces which are lying above the column 1 or within the column first comes into action, and I have denoted the direct stresses in each and column by naming V1, V2, V3, V4. Similarly for second story, V1 dash, V2 dash, V3 dash, V4 dash, and for third story, V1 double dash, V2 double dash, V3 double dash, V4 double dash, and dashes are for just for for recognizing that these stresses are of first story or second story or third story or fourth story, sorry, for third up to third story. And these, and one thing more, these V3 and V4 stresses are in opposite nature. Sorry, V3 and V4 forces are in opposite nature to V1 and V2. If V1 and V2 are tensile, then V3 and V4 will be negative, sorry, that is compressive. I hope you understand. Means V1 and V2 are tensile, V3 and V4 will be positive, and V2, V1, V2, V3, V4 are our axial forces. So let us calculate the value of V1. And how we can calculate the value of V1? We need to consider the moment about this neutral axis. This is our neutral axis or point of contraflexure. So if we, and I have missed the load here, we have loading on here, that is 12 kilonewton. This is 24 kilonewton. Similarly this is 48 kilonewton. So if we take moment about this point of contraflexure, so we will have here 12 multiply by, and the distance of this 12 kilonewton from this NA is 6 plus 6 plus 3, means 15, plus the second is loading is 24 multiply by 6 plus 3, 9, plus 48 multiply by 3, and distance of this V1. See here, we for calculating the moment, what we apply the force with perpendicular distance, and see here guys, our V1 is parallel to this neutral axis, means there is no any distance, perpendicular distance with this force V1. So V1 will be multiplied with 0 because the distance is 0. Similarly plus V2 will also take clockwise moment, so plus V2 multiply by, and the distance of V2 from this NA is 5 meters, so 5. And see here guys, V3 and V4 are taking anti-clockwise moment, so it will be negative. So minus V3 multiply by distance of this V3 from this neutral axis is 10 meters, so 10 minus V4 multiply by span is 15. It will be equal to 0. Now on solve this, we will get minus 16.65. One thing more, before you doing this, what we need to do is write one more step, then it will be more clear. I am rewriting this 12 multiplied by 15 plus 24 multiplied by 9 plus 48 multiplied by 3 plus this becomes 0 plus V2. Now what we need to do is we have to substitute the value of V2 in terms of V1, which we have calculated in step 1, which was, see here, V2 equals to 0.33 V1. So our V2 will be 0.33 V1 multiplied by 5 and negative, and V3 is 0.33 V1. So negative 0.33 V1 multiplied by 10 minus V4 is equal to V1. So V1 multiplied by 15 equals to 0. Now resolve this, then we will get minus 16.65 V1 plus 540 equals to 0. Now here we will have V1 equals to minus 540 divided by minus 16.65. On solving this, we will get value of V1 equals to plus 32.43 kilonewton. Positive means here tension. Similarly, now after getting the value of V1, find the value of V2, and we have V2 equals to 0.33 V1. So it will get 0.33 multiplied by 32.43. Then we will get here 10.70 kilonewton. That is also tension again. Similarly, we have V3 equals to 0.33 V1 equals to 0.33 multiplied by 32.43. Then we will get here again 10.70, but this time it will be compressive because our V3 is opposite nature of V1 and V2. V1 and V2 are tensile, so V3 and V4 will be compressive, and we have V4 equals to V1. So V1 will be, we have already calculated the value of V1, that is 32.43. We can also apply the check, that is V1 plus V2 will be equals to V3 plus V4, or some difference of V1 plus V2 and V3 and V4 will be equals to 0. If we add V1 and V2 and V3 and V4, and see here what we can do here, we can apply a check. We didn't got much different, we are getting similar value because the span was similar, but this check will be helpful for you guys to trace the mistake when the span is different. So at that time we can apply a check, that is V1 plus V2 minus V3 plus V4 will be equals to 0. We do not need to put the sign here of compressive or tension. Simply add V1 and V2, and after adding V1 and V2 subtract V3 plus V4, then we will get 0. It will be valid in each and every step. Now let us calculate the axial force in column of story 2, and that will be our step 3. So axial force in story 2, and again while calculating the axial force in story 2, we need to consider all the forces that is acting above the story 2 and at the story 2. So here there are two forces, 24 kilonewton and 12 kilonewton, and these direct stresses, that is direct axial force, that is V1, V2, V3 and V4. So we need to take the moment about the point of contraflexure. This is our point of contraflexure, which is at the mid span of the story second, that is half of 6 meters, so 3 meter, and spacing between the two columns is 5 meter, which is similar. So if we take moment about this point of contraflexure NA, then what we will have here, write a line here, taking moment about the point of contraflexure, point of contraflexure. We will have 12 multiplied by 6 plus 3 meter. So 12 multiplied by 6 plus 3 means 9, plus this is clockwise moment, and 24 kilonewton also taking clockwise moment, so 24 multiplied by 3. And see here guys, V1 and the distance, and the V1 is at 0. There is no any perpendicular distance for the V1, so positive V1 dash multiplied by 0, and V2 is at 5 meter from this neutral axis, 5 meter. So we will write here plus V2 dash multiplied by 5 meter, and V3 and V4 are of opposite nature, V3 dash and V4 dash, so minus V3 dash multiplied by 10 minus V4 dash multiplied by V4 dash multiplied by 15 meter, and it is going to be equals to 0. And one thing more guys, V1, V2, V3, V4, each and every column are representing our axial forces, and that force we are calculating in for each and every column one by one, and I'm showing this just for representation, that we have calculated this now this in step 2, and now this in step 3, and further in step 4 we will calculate V1 double dash, V2 double dash, V3 double dash, V4 double dash. So that will be our final step. And again the step is same here. I'm going to rewrite this 12 multiplied by 9 plus 24 multiplied by 3 plus 0 plus V2 in terms of V1 is again 0.33, V1 dash multiplied by 5 minus V3 is again 0.33, V1 dash multiplied by 10 minus V4 is equal to V1 dash multiplied by 15 equals to 0. And these are from step 1. So on solving this we will get, so we will get V1 equals to 10.81 kilonewton, which will be our positive. So we need to calculate V2 equals to 0.33 multiplied by V1, and put the value of V1, we will get V2 equals to 3.57 kilonewton. Similarly V3 is again 0.33 multiplied by V1, so it will again be 3.57 kilonewton, but of opposite nature from V1 and V2. Similarly V4 will be equals to 0.33, V4 is equal to V1, and it is going to be our 10.81 kilonewton. This is tension, this is tension, and this is compression, this is compression. Now time to move toward step 4, and in step 4 we will calculate the axial force in story 3. So here comes the step 4, axial force in story 3, and we need to consider all the forces that is acting on story 3. So story 3 is acted upon by the lateral force 12 kilonewton or the horizontal force 12 kilonewton, and these axial forces V1, V2, V3, V4. So I need to again take the moment, and the point of contraflexure is half of the height of the column, that was 6 meters. So half of 6 meter is 3 meter. Point of contraflexure is at 3 meter. So again we need to take the moment about the point of contraflexure, taking moment about point of contraflexure. So we will have here 12 kilonewton is taking clockwise moment, so 12 multiplied by 3 and plus V1 double dash multiplied by 0 plus V2 double dash multiplied by 5 minus V3 double dash multiplied by 10 minus V4 double dash multiplied by 15 equals to 0. Now solve this. Means we need to put the value of V2, V3, V4 in terms of V1, which we have been doing in step 2 and 3 also. So I am directly writing it here. Similarly, we have calculated the value of V1. Once you go through this step, it will be clear. Now we will calculate the V2, and you will get V2 equals to 0.33 multiplied by V1 double dash. Then we will get here V2 equals to 0.71 kilonewton. Similarly, V3 double dash will again be 0.71 kilonewton. And V4 V4 double dash is equal to V1 double dash, so it will be equals to its value will be equal to 2.16 kilonewton. This is tension, this is tension, this is compression, and this is compression. Now time to move toward step 5. So we need to calculate in step 5, we need to calculate the shear at end beams, and I'm going to use this diagram here. Let me write the naming. then I will use this diagram. So guys, what we need to do while calculating the shear at in beams, suppose we are calculating the shear at E. So in that case, what we need to do is the axial forces which are moving toward the point E or joint E will be taken as positive, and the force which is moving away from E will be taken as negative. So I am going to write here shear at E will be equals to, now see here in the diagram, V1 double dash and V1 dash are moving towards the point E. Similarly, V1 is moving away from the point E. So V1 will be negative and V1 double dash and V1 dash will be positive, and V1 will be subtracted from this value, and we already know the value of V1 double dash, V1 dash and minus V1. So put the value and find the answer. So this is what we get the value of shear at E. Similarly, after E, find the shear at F. And again at F, what we need to do is this. We need to take V2 double dash, V1 double dash, and V2 will be subtracted. V2 will be subtracted because it is moving away from the point F, and these two are moving toward the point F. So it will be positive. This will be negative, and this force will also come into action. So we will write here shear at F equals to minus 19.46 plus V2 double dash plus V2 dash minus V2, and solve this putting the value. So this is the value of shear at F. Similarly, shear at G. So shear at G, this force will come into action. So minus 25.88, and at G, V3 is moving towards G. See here, V3 is moving towards G, and V3 dash and V3 double dash are moving away. So V3 will be positive, and V3 dash and V3 double dash will be negative. So positive V3 minus V3 dash minus V3 double dash. So it is going to be minus 25.88 plus V3, and put the value of V3. So here is the value of shear at G. Similarly, shear at H is equal to, this force will come into action, minus 19.46, and at H V4 is moving towards, so positive V4 minus V4 dash is moving away, minus V4 double dash, and put the value and find the answer. You will get 0. Similarly, shear at I. So see here diagram. We are calculating shear at I, and at I, V1 is moving away and V1 double dash is moving toward I. So V1 double dash will be positive and V1 dash will be negative. So V1 double dash minus V1 dash. Put the value and find the answer of the shear at I. We will get 2.16 minus 10.81, which will be equals to minus 8.65 kilonewton. Similarly, shear at J will be equals to minus 8.65. V2 is moving up, V2 double dash is moving towards J, so positive V2 double dash minus V1 dash is V2 dash is moving away, so V2 dash, and put the value minus 8.65 plus 0.71 minus 3.57, which will be equals to minus 11.51 kilonewton. Similarly, shear at K will be equals to minus 11.51 at K, V3 dash is moving toward K and V3 double dash is moving away. So positive V3 dash minus V3 double dash, put the value and find the answer, minus 11.51 plus 3.57 minus 0.71, which will be equals to minus 8.55 kilonewton. Similarly, shear at L will be equals to minus 8.55 and plus V4 dash minus V4 double dash toward away equals to 0. Similarly, find now time for the shear in the final or the third story, that is shear at, we will calculate accordingly shear at M and OP. So shear at M will be equals to at M V1 is moving away, so minus V1 double dash, so it will be minus 2.16 kilonewton. Similarly, shear at N equals to minus 2.16 and V2 is also moving away, so minus V2 double dash, which will be equals to minus 2.16 minus 0.71 equals to minus 2.87 kilonewton. Similarly, shear at NO is equals to minus 2.87 and plus V3 double dash, so it will be equals to minus 2.87 plus 0.71 and we will get minus 2.16 kilonewton. Similarly, final value of the shear now, and that is shear at P equals to minus 2.16 plus V4 double dash, and it will be 0 kilonewton. Now here comes the step 6, and in step 6 we need to calculate the moment in beam, and for calculating moment in beam we have a simple formula, and that is multiply the shear in beam with half of the span. Suppose we are calculating the moment in beam MEF, then it will be given by shear in beam EF multiplied by half of span of beam. So we have shear in beam EF equals to minus 19.46 multiplied by span is 5 divided by 2. So on solving this we will get minus 48.65 kilonewton meter, and same is the step for each and every beam. So I am going to provide you directly the value of each and a moment in each beam directly here. So guys, these are the values of the moment in each and every beam, and I hope you enjoyed this lecture about the cantilever method for the solution for analysis of the frame. And stay connected with Civil Learning Online for more videos related to different subjects for the civil engineering. Till then, stay safe and take care of yourself. I will be back soon with a new video, a new topic.